Okay. Good morning to all the participants and the experts who are there in this meeting, and head of the Department of Chemical Engineering as well as the Faculty of Chemical Engineering. The department feels proud to introduce the expert for day 1, session 2, the following session, Dr. Uttam Doraswamy. Dr. Uttam is an alumni of the Department of Chemical Engineering, B.M.S College of Engineering. So I request all the participants to give him a big round of applause. We are very proud to have you, sir. So Dr. Uttam pursued his chemical engineering at B.M.S College of Engineering, went on to do his master's in chemical engineering from Imperial College London, and then PhD as well in chemical engineering from Imperial College London. He's currently the founder director of Elxion Private Limited, which is a startup in the area of e-waste management located in Bangalore. This organization is focused on developing ethical and sustainable practices and processes in a largely unregulated market space. Sir holds 6 US patents in engineering design and material science and has published over 12 papers in peer-reviewed scientific journals. He, prior to his founding this company, he has worked on developing new technologies for the production of synthesis gas based on oxygen transport membranes for Praxair Incorporation at the Praxair Technology Center in New York. A warm welcome to you, sir.
Hello, everyone. So, thank you to this college for giving me today. Thank you to Puttaswamy sir for taking the time to put together this program. I think some of the other speakers have already commented on how difficult it is to chase people, myself included, to make time to share these things with, I think, close to 200 people today. So these virtual platforms, even though they are difficult to manage and a sign of our times, it does give a things move to a low-cost kind of online platform. So I guess there's some on trying to understand this directional change that industry is expected to make and society is expected to make to bring in circularity or sustainability in multiple areas. And one of the low-hanging fruit in that process is waste management. So I think opportunity
Uttam, your voice is breaking.
Voice breaking, sir. I have some interference from some other sound as well.
Okay, I'll unmute all. Now it's clear. You can go ahead.
I can go ahead? Okay.
Yes, it is clear.
Great. So I think is that as teachers, all of you have a chance to have a huge impact on your students. And so whatever you can take out of these programs and pass on to the students, I mean, I think the opportunity for this audience base to have an impact is immense. I always start with a couple of slides on e-waste, right? So what are we talking about? So what I've done here is taken news articles between 2017. People are talking about, or what are the words that are most common when people talk about e-waste? And the way the word work, it associates the size and the color or the emphasis inside the word cloud with the number of repetitions. For those who are interested, this was done in R. It's very easy to do. And you can see that there's some e-waste, the most word. Now to talk about it, because a lot of people are understanding that this is a problem, understanding that we need to address it. And I always find the second and third rows to be the most interesting, because that's what people are saying somewhere in the middle of their thoughts. And so you can see that they're talking about being market, manufacturers, consumers, informal, unorganized, problems. So what yeah, look at what the problems are. And the second and third rows in the word cloud will capture what the problems are. And we'll look at that in some more detail. But before we do that, just for everyone here, that it's pretty simple. E-waste is just anything electronic when it reaches end of life. But that's a loaded statement. They're all to blame. You can't kind of always, and my kids got old phones, and there used to be a time 20 years ago when you had a cordless phone and you were, had made it in life, and you phone. Now you've got webcams, cell phones, weighing scales for baking, home tools. And so almost everything in our life is somehow now having a touch point to electricity. And like all things, when they die, they end up being more complicated than some things we've heard about from our previous speaker. And the reason for this is that in order to make our life easy, we have packed these things with complexity. And I'll talk a bit more about that. So actually, e-waste, if you really want to break it down, all you have computing and communication equipment. These are your computers, your as called IT and telecommunication. You have domestic appliances, microwaves, fridges, air conditioners, those kind of things. So those are called lamps, screens, LCD screens, LED bulbs, new lighting systems coming out every day. And so we don't know where to place those, so we place them in another category called screens. But this is just the starting point, because beyond this, there are so many uncategorized equipment, control panels, electricity supply grid, solar. Solar panels are not covered by today's e-waste rules. So we're talking about e-waste plus photovoltaics being a separate category on their own. And toys, we have toys don't feature on the current government rules explicitly, at least, at all. But toys form a huge part of the e-waste that we're seeing. Cables, wires, chargers, adapters. So the list went on. Now, why is this a problem? Because where we've understood, or where we are coming from, and sneaking behind that, but is showing no correction in terms of our appetite. So the first time that a report was put together, I think the first big report came out in 2007, UN report on e-waste. And at that time, if I'm not wrong, it was 44.7 million tons. It's been 2 or 3 years for the next report. I just changed this number last night, and it's 53.6 million tons. So e-waste is that people are already trying to correct the curve for plastics or correct the curve for packaging. In e-waste, the curve is not correct. We're on a linear growth path. And what's happening is that the rate of consumption per individual, which also has to grow in order for the total to grow, is also growing alarmingly. The global average, the latest figure for 2020, which is not on this, but it should be here, is over 7 kg per individual. That means across the world, every single one of us owns at least 7 kg of products that are scheduled to be disposed. This may seem shocking, because you think, well, I don't really have that much electronic waste to be disposed. But when you think about it, you own a share of a fridge, you own a share of a microwave, you own a share of a lot of heavy equipment, potentially an AC. All of you have some cables lying around, 2 or 3 old phones, an old music system perhaps, tape deck. And you will reach 7 kg very, very quickly. And I'm saying that even the people across the world who you think don't have electronics are contributing to this number. So there are some people who own 30, 40, 50 kgs for this. Climbing. We're talking about 5,400 Eiffel Towers worth of e-waste being dumped every year. And unfortunately, these are not even at 20%. So it landfill, the questions are open. In countries, India very rarely gets dumped because there's still some value in it. But in the developed world, often this will make its way to landfill. And talking about a huge loss of value because we're not able to recycle it. If you look at India a little closely, and I like doing this because we are on a growth trajectory economically. Now, COVID may be a bump in the road, but the expectation is that our consumption market is expected to grow and fuel the years. Heavy waste. We produce only about 2 kg per individual, maybe a little higher in the latest report. The kind of market leaders in terms of voice break. Am I still clear? Or?
Yeah, I think there is a voice break. Sometime it is all right. Sometime there is a break. Actually, I don't know. Maybe problem from your side, or I don't know.
Maybe with the mic. I will try and stick closer to the mic, and maybe.
Yeah, please.
So, in India, this is a big problem because we expect this number to reach the global average. And that would mean that our e-waste is going to grow 2 to 3x, maybe 4x. And once we reach we don't have the capacity to handle today's volumes. So what happens when we reach to more volumes? In terms of rules, I think the previous speaker was talking about specific rules for biomedical waste, specific rules for industrial waste. Well, it has made specific rules for e-waste. And these were notified in 2016, entered under the Environmental Protection Act in 2018. And actually, we are all obligated to follow these rules. But they are more strict for bulk producers or sellers of electronics and then bulk consumers. But I think the rules are probably less important to this. But what they are trying to do is to put pressure on producers and consumers. These are companies, education institutions. B.M.S college, for example, qualifies as they have to follow rules how they dispose their end-of-life electronics. So producers are those who sell electronics under their brand. This would be Sony, LG, Xiaomi, Apple. Bulk consumers would use electronics in high volumes. Educational institutes, corporates, back office companies, hospitals, hotels. The rule, I believe, is 1 crore and 20 employees. So the catchment is very, very big. what happens? I guess you can see the screen, right? Demanufacturing overview. So ultimately, when you break these down, these are the components that you are able to see easily. But as we dig in, we'll see that this is just the first level of breakdown, and that there are much more components embedded in there which have a large implication on both economics and risk. So, as I said, I want to take 2 slides to discuss this term of circular economy, because there's a lot of talk about this and how we need to reach it. But I have some views on this, which I'm happy to share, and I think that this is more complex than just a diagram. But what they talk about in a circular economy, and if you can follow me here, is that the first thing they're going to is they're saying that they want to reduce or cut down the primary usage of materials. And once it goes through its use cycle, increase maintenance, increase reuse, increase refurbishing, maximize recycling, increase the symbiosis with industry so that the material loops back to the beginning before the primary stage, and try to minimize anything leaking out of this boundary into whether it's energy recovery, this EFW is energy from waste, or landfill. So this is, it looks like a complex diagram, but the next slide really shows us what we should be doing. So this is what we've been doing for many, many years. Taking things out from the system and then throwing them out when we're finished. Today, we are somewhere here where we're taking some things, we do some paper recycling, we've started doing some plastic recycling, but we throw out a whole bunch of stuff. In a circular economy, in principle, we throw out nothing and everything loops back infinitely. But this has a catch, because this will only work for finite demand. If demand is linear, then the process can't be circular. And that's something that we all have to understand. So what are we talking about is embedded inside e-waste. And when you look at a periodic table, anything that you see highlighted in a grid is available in electronic waste. So you can see that almost 60-70% of the periodic table of elements is covered by e-waste. You have everything in green is a precious metal. Everything in blue, I think, is critical. So those are metals which are very difficult to source or have supply limitations. So e-waste is embedded with many, many valuable things. And a simplistic calculation was that there's about $57 billion worth of metals and recyclables in the e-waste stream that we are disposing annually globally. $57 billion. It's always difficult to visualize this. So I took that data and then I said, let's look at things that are easy for us to understand, right? We all love gold and silver. Well, we are probably losing sight or disposing or unable to track over 200 tons of gold a year, 1,200 tons of silver. And in the metals that we use every day in electrical wiring, and in our drinks and beverages, in our aircraft, and in our houses, 20 million tons of iron, 1.8 million tons of copper. These are things that are leaking out of the system to we don't know where right now. What does this mean for India? We've heard a lot about political instabilities we're having with our neighbors. We've heard a lot about trying to become more self-reliant. Well, just a snapshot of where we are today. So India's year-on-year copper imports more than doubled. And so today we're a net importer of copper almost to the tune of 100,000 tons. Now, this has something to do with Thoothukudi and the problems we're having in that smelter, but it's beyond that. Our demand is growing very strongly, but our supply is stagnant or actually decelerating. We are amongst the largest importers of gold along with China. We alternate. We import a huge amount of gold every year. We import $4.4 billion worth of aluminium, and we have 25% exposure to China in aluminium alone. And this is just the start of the story. Beyond this, there are PGMs, rare earths, battery components, metals embedded in lights, LCD screens. And we'll talk about some of those in due course. But the situation for us is that this is now a critical area. And I have been privy to some of the discussions that this is something that the government is taking very seriously. For the first time, we're putting in a metal security policy. This is going to be led by the DRDO, and the government is looking very, very carefully at trying to make sure that we are self-reliant on the materials that we are likely to require for our manufacturing aspirations. And this is very important because if we aspire to be a manufacturing hub, and the raw materials and the control of those raw materials is critical for us to be successful there. So this is just data from Alexion. This is from our recycling operations, and you can see that the numbers that are coming out of the reports are very similar to what we get in the field. Iron and steel form a bulk of the recyclables. About 25% of the iron and steels you'll see in aluminium. Half of the aluminium you'll see in copper. And what's not shown in the report, because it's not an area of focus, is that a significant portion is plastics. Now, I'm not going to spend too much time on plastics in this presentation, but that's a completely different animal. And the range of plastics nowadays is almost as complex as the range of metals and alloys. And what is sad is that we see a significant amount of material, and this is, reaching up to 10 tons over 2 business years, that continues to go for landfill or incineration. Now, this is not because we want to do it or it's business, it makes business sense, because both these are cost items for us. When it says TSDF or incineration, as a business, we are paying for this. So we want to avoid this, and we do everything we can to minimize this. But there are certain materials that have no remaining value, and these need to be sequestered. And unfortunately, this number is not as small as it should be. So I'm going to take one slide to look at where we are in terms of the circularity. So I'm going to say that, we want to be circular. The Europeans have a lot of copper production in Sweden, in Belgium, and they have some of the primary copper production, and they do a lot of work in secondary copper. So they're a good example. And copper is the most recyclable material in the sense that 100% of copper can be recycled. You have zero loss. Whereas in the case of aluminium, for example, in the recycling process, due to the formation of dross, you will lose about 2% of aluminium every time it goes through one loop. In copper, Europe produced about 4.1 million tons of primary copper. And if you look here where I've highlighted in red, they were able to recover about 2 tons from a combination of factory scrap and end-of-life scrap. So we are looking at only about 50% circularity in the world leaders. So these are the best smelters in the world, Boliden, Arubis. These are all industrial leaders in terms of efficiency for copper, and industrial leaders in terms of recycling rates. Yet the overall picture is down at 50%. So this tells you that there's a huge opportunity to increase our supply from secondary sources and minimize our dependence on primary sources. And I'll go through a few reasons why we should be doing that. So there are 2 things you have to think about when recycling. One is that, of course, you don't want to waste something. When you throw something out, we've all been brought up to minimize waste, and you don't want to throw something out. But there is a very direct link with the environment and climate for not throwing something out. And this link is often not economically budgeted. And this is why recycling often suffers when you look at economic analysis. So let's look at aluminium on a 100,000 ton basis. So if you wanted to make aluminium, there are 2 typical processes. You can go pyrometallurgical all the way, but nowadays, the standard is that you will start with your ore, and then you will do the Bayer process. You have electrolysis, and then you cast your aluminium. In the secondary process, your aluminium is relatively pure, maybe diluted with some magnesium. And this is either refined if you're trying to remove impurities, or simply remelted by remelters and then cast. Now, when you look at the energy demand on a 100,000 ton basis, you are using about 4,700 terajoules of energy for your 100,000 tons manufactured from the ore, because you are trying to reduce its oxidation state from 4 or 6 or whatever it may be down to a metal. Whereas in the case of scrap, you only need the energy required to remelt it. And so you are down at 240 terajoules. The implication of this is that you are saving almost 350 kiloton equivalents of CO2 for that much aluminium. Now, aluminium is going into our aircrafts. It's going into our Pepsi cans. It's going into our MacBooks. It's going into things that you and me touch every day. And so these decisions we make with the things that we have in our hands have huge direct environmental impacts in terms of CO2 mitigated. The story is not different with copper. So even in the case of copper, if you go through the primary process, and you go from the copper ore to the copper cathode, which forms the basis for purification of copper, and whether you do this by purely pyrometallurgical process or hydrometallurgical processes, you end up with significant savings of putting in your raw material from scrap, because you do not have to concentrate it, you do not have to purify it, and only 30% of the energy is required to bring your copper to the market when you bring it from secondary sources. So this is huge environmental impact because demands for copper and aluminium are continuously climbing. Now, I wanted to shift tack a little bit and talk about critical materials. So copper, we understand, aluminium, we understand, iron, we understand. These are things that, we've been seeing for our generations, and, to be more honest, for civilizations and millennia, we've dealt with these materials. But life is much more complicated now. So I broke down life in terms of 4 brackets, and I'm sure there are more brackets, but these are brackets that touch most of us today: mobility, energy, communication, and defense. And then I said, let's look at how we've gone and complicated things from a materials perspective. So I didn't start with the horse, which would have been in some way more complicated if you consider the biology. So I decided to stick with the mechanics. We had cycles and steam engines. You were looking at 1 or 2 metals, coal, water, 1 metal in a cycle. Now you've got aircrafts which have all sorts of metals in the engines, in the avionics, in the controls. They're critical materials required just for coating the engines, and metals whose names I forget. I had to write them down before today's presentation. I'll show you the fact that I wrote them down. They're so complex. I didn't learn about them when we were, when we went through school. With energy, it was the same. You had 1 or 2 sources of energy: coal, maybe coal gas, maybe oil. Even as far as petroleum was fairly simple. Now with renewables, you're looking at very complex materials inside solar photovoltaics. You're looking at direct drive motors in wind turbines, which require rare earth magnets for them to function. Defense, it was good when we had a nice sword. The huge breakthrough was whether you had iron or whether you had steel. But now, recently, America had to go back against their own law because they couldn't get the materials they needed for their F-35 because of their sanctions against China. So the American Department of Defense violated American law to source materials for their F-35. Communication is another great example. We had letters, we had pigeons. Now, with the internet and phones, critical materials have become an important aspect for all of us. If you look at what they are, so critical materials are basically materials that are of economic importance, but have a supply risk. And the supply risk may be the fact that the availability is low, or the availability is in a region of geopolitical risk, or it could just be that we don't have production capability for it, and so we're exposed economically if we require it. So if you throw all these materials onto this chart, you can see that you start seeing things that come into this quadrant. They're economically very important, but they have a very high supply risk. So these materials then become things that have to be focused on. Now, this is specific. This chart is specific to Europe. I'm not aware of anyone doing it in India, even though there's a rare earth institute, I think it was instituted in the 1950s. I'm not sure how active they are, and I know that our production capacities are very low. If you look at just the energy space, and you look at the rare earths there, you see these two, neodymium, dysprosium, these are both part of very strong magnets that are required for direct drive motors. Most of these are catalysts or part of batteries. These two are used in screens. This is again a catalyst. And so you have right at the top, very critical, where the supply risk for us is very high. If India wants to go electronic for their vehicles, if they want to go fuel cell for their automotive and standalone power, we have a lot of exposure to critical materials in the production chain that we don't have control of. The other aspect of criticality is that maybe materials are available in countries that don't have production scales, like, for example, cobalt, which is used in almost all new age batteries, rechargeable batteries, is largely from the Democratic Republic of Congo, which even now is controlled by often militias, has child labor, and very geopolitically unstable. And this means that you are planning your future automation, your future mobility, your future battery requirements on a material that may or may not be available tomorrow. As often, I find that Dilbert hits the nail on the head. And what do you do about this? What are we going to do? And this cartoon basically says there's a consultant who says China has most of the rare earth materials, and one of the options is trying dying and reincarnating. There's 20% chance you'll be born Chinese. And what's plan B? Well, if you don't do it the first time, try dying again. So that's how serious the situation is, and especially with our current geopolitics, the whole world is trying to rebalance the supply of critical materials out of China. So I put this graph again so that you can see that I have showed you that all these materials are important and all these materials are in e-waste. So one of the important streams that is going to enable us to try to correct our dependence on these materials is going to be our own waste streams. And it is imperative that we start to treat these as resources, because even a single molecule of these materials that is wasted is going to be very expensive for us. And there are two reasons for this. One is we may not be able to mine these materials naturally. And the second is that a lot of energy has gone into coagulating these materials into a very small stream. And we should not waste that energy that has gone into making and purifying these materials and using that, losing the opportunity of grabbing them as a secondary resource. So we all agree now that, e-waste has a lot of good things, and if we do our job correctly, there should be healthy economic benefits. So then let's spend a few slides looking at how well we're doing in actually gaining all these benefits that I've been talking about on paper. So what happens to e-waste? Secondary resources are not well recycled in most developed countries. Europe is doing the best job of all of them, and their flows are a little bit low, but America, Japan is doing a lot better because of the Olympics, but and because culturally they're bringing recycling back into the main framework. But otherwise, most of the e-waste flows from developed world into illegal processing hubs in Africa, China, and to some degree India. Now, China has introduced probably the most stringent import ban ever seen under the National Sword program that is stuck, literally a tsunami in the recycling world. They did it a year or two ago. India has a long-standing import ban since 2011, I believe, but its enforcement is very weak, and so there is still leakage. But what happens is when these two become difficult, then most of the material ends up going to Africa, where legislative frameworks are still weak and enforcement frameworks and corruption are even worse in some cases than Asia. So if we look at India in particular, we generate about 2 million tons of e-waste. When I look at other registered recyclers like myself, the capacity coverage is not even 18%. So even though there's supposed to be 700 million euro worth of materials, there's only about 18% registered capacity to treat that waste. And as we saw, it's growing at 14% a year. So when you reach, the next target, 2021, 2022, it's 9-10 million tons, and it's $4 billion of valuable metals. Are we ready, and do we have the capacity to extract those metals? And the answer is no, we're not. Because today, out of that 2 million tons, 1.6 million tons disappears into an informal sector that we don't regulate, that we don't have any control of. And to be honest, we don't know what their returns are and what their environmental damage is. And so if things go as is, then you're going to have potentially 8 million tons of e-waste just disappearing from the formal and track system over the next few years. Why is this? So I put this chart, and this chart I made specific to India. We have a strong history of recycling. We are a recycling country. We have traditionally avoided waste. We have lived close to our roots. We know how to reuse things. But what has happened is that the complexity in the world has gone so quickly that society has not had a chance to learn how to reuse and recycle those things well enough. And so when it comes to e-waste, let's look at this pyramid to see what we can do. Can we avoid it? We should, but it's increasingly difficult because the government wants to digitize more things. Everything is going to come on your Aadhaar OTP. You have to have a phone. I'm talking to you on 2 laptops because the first one was not good enough. So, are we going to reduce it? I doubt it. Can we reuse it? India does a fantastic job of reusing. We reuse, we resell, we fix, and we do probably the best job in the world in keeping this market active. We do a good amount of recycling. We may call it informal, but I don't see metals, copper, aluminum in your solid waste. Nobody's complaining about aluminum lying in the landfill because somebody's livelihood is dependent on taking that value out. So we do a great job in recycling, but we are very, very bad at the bottom of the pyramid. We do not recover, we do not treat, and we dispose typically very badly. So we do not sequester, we don't understand the risk of critical materials, heavy metals, mercuries, and we tend to be very callous in how we're disposing hazardous materials. And so I want to emphasize that as much opportunities present in e-waste, there's also risk. And these things travel together. And if we look at only the opportunity without the risk, then we're looking at the picture very imbalanced. These are a snapshot of the dangerous components of e-waste. It is not complete. It's just to give you an idea that these are the nasty things that's there. The plastics, the PVCs can lead to dioxins. When you have burning of plastics in Delhi, or when you're burning cables for recovery of copper, that's one of the biggest contributions to Delhi's air pollution. You have lead in solders, you have cadmium, antimony, arsenic, chromium in all the coatings on steel, often in the form of chromium-6. You have polychlorinated biphenyl in many capacitors. And so there are many, many nasty things. Mercury in lights, in CFL bulbs, in significant amount of mercury. And we look at a case study in a later slide. And so when we deal with this, we have to understand that there is recovery potential, but there's also an obligation from recyclers to try and minimize the impact on the environment from the things that we have collected from mines and concentrated in the things that we like to use. So the CFL example is a good one. There are approximately 4 to 5 milligrams of mercury in a single CFL bulb. When you consider old tube lights, this number can be as high as 60 milligrams. And an interesting study has been done by an NGO called Toxic Links, for those who are interested, where they sampled and tabulated the mercury across different lights. And so when you look at a single office, I've worked with these lots many times. I did a government lot which was 10,000 full tube lights. So this is not a lot. 2,000 units is just a medium-sized office. If you just dispose that to somebody and he takes it and throws it away in, for example, the Vrishabhavati Canal, which happens a lot. I'm not just saying that. It happens a lot. If you look at the CPCB norms for pollution in water, and we have experts who know about this more than me, that's about 5 million liters of water that are now unfit to drink if that mercury is able to leach into that water stream, which it will eventually. So you could be taking out drinking water for millions of people by making a poor decision about how you throw away tube lights. And these are the connections that we need to make to understand what potential impact we're having on an environment. We tend to forget about things when they're not in front of us. So we dump this e-waste in Africa, or in India. I removed the India slides, but we dump these things in Africa, and what happens there? Somebody's trying to make money on it, and they don't know how dangerous it is. And so you are taking a toxic stream, and then you're exposing a third party to that. And the consequences are written in the slide. They're terrible because everyone has heavy metals in their bloodstream. The children are going to get lead exposure, which affects their neural development. And so you are not only damaging the environment, you're damaging other societies. So why don't we do it formally? Why don't we do this in nice factories? And just like in the case of biomethanation or anything else, economics, if you want to deal with a very complex stream, you often require a very complex flow sheet. And we have spent, imagine how complicated Intel's process is to make a single chip. And then we think that, we can recycle that using, I don't know, something very simple. It's not possible. If it's complex, the recovery chemistry will always be complex. And that comes with a great cost. The other problem is that in waste, the unpredictability of the raw material means that your capital equipment has to be sensitive to all kinds of raw material, all kinds of variability. And this makes it even more challenging because now you're not only looking at a capital process, which is intensive, but you have to have great technical depth. So even in wastewater treatment, and I'm sure our next speaker will talk about this, everything seems simple, but unless you manage the waste treatment line, unless you actively understand how it's doing and make the minor adjustments, you are not going to get the process performance that you want. But how do you do that if you don't have the technical depth? And one of the biggest gaps in today's market is the availability of technical depth. We have given all this waste to people who do this illegally somewhere. How many engineers, how many doctorates, how many chemical engineers are running out of their universities and joining a waste treatment or a recycling business? The answer is probably very, 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 very small. So this is one case study, and this is a case study I put out on my presentations because it's actually quite a shocking case study. I lived very close to this. So I lived maybe 2 or 3 miles from Love Canal, and we didn't hear about it. When I was in that area, they used to call it Cancer Street. And I never knew why they called it Cancer Street, but the history is very interesting. So a 70-acre piece of land was bought by a real estate development company in, I think it was in 1890s, and they wanted to develop it into a township. And the reason for that was the Niagara Falls was very close by, and it was a source of power. At that time, the only power that was available at large scale was from the hydro process at Niagara Falls. By the time they dug the land up and they were ready to sell the plots, alternating current had already come, power was being distributed across the country, and there was no reason to be close to Niagara Falls. So the land value crashed. So they decided to sell that land, and it was bought by a hooker chemical company. They buried 20,000 metric tons of chemicals completely legally with the permission of the government, all sorts of nasty chemicals. They buried it into the ground. And once they realized that it was getting unstable and this was not a good idea to continue to own it, they sold the land to a government school board for $1, including the liability. And what happened? 30, 40 years later, all those chemicals started coming out of the ground. Everybody had birth defects, cancers, the death rates in that area were terribly high. And then the government had to step in to clean up that. And this led to the formation of what is even used today, the government super fund. And it was used for hurricanes, it was used for Hurricane Katrina, but the origin of that super fund is this issue. It took them 21 years and $400 million before they could clear literally a half-acre plot. So you can imagine how expensive it's going to be and how difficult if we don't control our disposal today. When we talk about putting it into this quarry or that quarry and forgetting about it, you can't forget about it. And someday it's going to hurt you. And when it hurts you, it's going to hurt you very, very badly. So that brings us to the question of, sustainability. What does it mean? And I always describe this as a mathematical point. Sustainability is a mathematical point. It's a mathematical point from the solution of 3 things. You have to make sure that your social equation is not imbalanced. You have to make sure your economic equation is not imbalanced. And you have to make sure your environmental equation is not balanced. When you have a perfect balance between these 3, that point is your sustainable point. But we never look at all 3 together when we do an analysis of a project. Even if you do an analysis of a grant as researchers, you usually look at one of two. You make sure that it's going to be taken by industry, and maybe you make sure that it's not going to violate any government guidelines. Very rarely do we take the social into account. And there's a lovely quote by David Attenborough where he says, we have a finite planet. Two or three of us can leave this planet on a SpaceX module at a time, but the rest of us can't leave. So our planet is finite, but we've had a growth curve that's linearly upward for centuries. And anyone who thinks you can have an infinite growth in a finite environment is either mad or an economist. So economics will keep telling you more growth. If you have a problem, spur growth, spur demand. Even today, after COVID, what should the government do? Spur demand, increase demand. But if you keep increasing demand with finite resources, at some point, this sustainability doesn't make sense. You cannot be circular if your demand is linear. So what does this mean? It means that if you want to be circular, in my opinion, you cannot only address circularity. You cannot only address recycling. You have to address demand. Unless we can temper the demand and increase the recycling rates, circularity will remain a pipe dream. So this figure tells you that even if you recovered everything from e-waste, theoretically, you still need 14 million tons of additional resources just to produce the electronics we need. So suppose I took all the electronics that came for recycling and I took everything back. I'm still asking for 14 million tons of new material. How can I then be circular? The only answer is to temper demand. If demand can be tempered along with increase in recycling rates, then you can approach circularity. And so innovation is not only about technology. It's not only about finding new solutions, recovering more. Of course, that's part of the equation. But equally important is for us to innovate on tempering demand, because this is going to be the challenge of our generation and the next generation. If demand cannot be tempered, then we will have unmanageable situations in the future. So let's look at from chemical engineering teachers. What do we tell our students? Why should we ask them to look at this space more seriously? And where are their skills potentially useful? So all over this space is a chemical engineering footprint. Everywhere you look, you have a chemical engineering footprint. Whether you come to energy recovery, incineration, pyrometallurgical processes, burner designs, flue gas analysis, plume studies, stack studies, combustion kinetics, material stabilities. These are things that chemical engineers should and need to be doing. When you look at treatment and landfill, we have leach rates, leachate analysis, toxicity stabilization, monitoring, remediations. These are areas that we should be encouraging people to look at as gloriously as we do when they get a job at, for example, IBM to make a computer chip. We don't encourage them often to look at this as a success. He's working for a recycling company, or he's working for, I don't know, it's not as big a brand. But unless we do that, unless we can push our students to apply their energy and skills in the reverse cycle, then we are always going to remain imbalanced. Electrochemistry, recovery chemistries, plastics, metals. I mean, the space is full of a chemical engineering footprint, but it's our responsibility to make this space attractive, to show people what value they'd be adding by applying their skills in this place. And this is not the only thing. We are going to have require innovation beyond just technical innovation. We are going to require innovation in the entire reverse logistics chain. How do we finance it? How do we measure projects by taking into account the recycling? How do we design systems by taking into account recycling? So today, we don't do that. And that makes the recycling even more difficult. So there is, in all this bad news, there's a wealth of opportunity. And there's a wealth of opportunity for engineers. There's a wealth of opportunity for entrepreneurs. There's a wealth of opportunity for pure play business-minded people. But for that, we have to create the ecosystem. We have to incentivize people to look at it with more positivity than we look at it today. The last few slides are really a plug, and it's just a few quotes that I I like to think about, and I leave with people to think about, because these quotes are long-standing. And if we can think about things in that way, if we can think about the problems in the way that these people thought about them, they may influence how we address them. The planet and nature are a fine balance, and nature's worked for millions of years and removed many systems that affected this balance, whether they may be the dinosaurs, other mass extinctions have been tried and failed, and the system has evolved to achieving a fine balance. And we are tipping that balance today. And so we are playing a pretty dangerous game. And so the two quotes I like to think about. We've reached clearly a fork in the road, and there are two roads. And the road that we have not been traveling is probably the one that we need to look at more seriously today, and incentivize our students and our future generations to spend more effort there to correct the imbalance of the past. I bring in David Attenborough again. We've spent a long time in human civilization in trying to make things tame, in trying to collect people and urbanize them. And we've lost our connect with nature. And Attenborough says, no one will protect what they don't care about. And no one will care about what they never experienced. So we have to give the future generations the experience of nature for them to want to protect it. And only when they are connected will they see the value of protecting it. And therein lies our hope. So, it's not all doom and gloom. I think when we try, we do succeed. This is just a snapshot of some positive things that we've seen when humans try. We've tried to conserve the gorillas, they're back. We did a huge effort on whaling, and they're back. And people are now in UK talking about returning agricultural land to the wild. And down at the bottom, we have, two messages, I think, that will reverberate through the ages. That there's no point being disappointed. There's no point being downbeat. Human civilization has driven on hope forever and will continue to drive on hope. But we need to understand, the words of very wise people, that there is enough. But if we're not careful at understanding what enough is, and then we'll learn a pretty hard lesson. That's all I have. Thank you. I'm happy to take any questions.
Participants can unmute themselves and ask questions.
Sri Lakshmi Madam is there?
Participants can unmute themselves.
Sri Lakshmi Madam? Yeah, Uttam.
Yes, sir.
Thank you very much for your maybe extended talk. Actually, it was a very informative, and I think I'll leave it to the participants to ask questions.
Okay.
I can unmute. The participants can now. You can ask questions. Sorry, I am muted. I think I have to unmute. 1 minute. Unmuted all. Dear participants, if you have any questions, please you can rise or you can put it on a chat box.
Sir, Ragini Krishnan has a question. What is the process to collect the e-waste for recycling?
So, Ragini, that's a good question, because that's the first step, right? Typically, in companies, they have to show their disposal every year, and that disposal has to go to a legitimate recycler. In the case of domestic e-waste, because of the economic imbalance, individuals may have very small amounts. And so what do? If you have a company to come and pick up a very small amount, who pays for the reverse logistics? Often this is the biggest sticking point. And what we're seeing is that is what is blocking domestic e-waste from flowing into recycling channels. But nowadays you have companies, NGOs, I should say, such as Sahas. They are doing collection door to door, or you have e-waste drop boxes in, for example, Chroma. Even the BBMP is starting e-waste drop boxes in some locations, in post offices, in some metro stations. But the idea would be, my idea is that you collect these things separately. Try not to dispose them with your regular waste. First of all, differentiate them. And then make an opportunity to find somebody who either collects it or has a drop box or is a recycler around you. And you make a planned disposal with them, say, for example, every 6 months or every year. And this way, the reverse logistics can be borne by the disposer, and by integrating it in his schedule. We are not talking about a huge amount, so this is usually something that can be just put in the car or the back of the bike, and so that will take out the problem.
Any other questions from the participants? Feel free to ask questions, please.
Uttam?
Yes.
I am Ravi Shankar here. How are you?
Good, sir. Good, sir. How are you?
Good. Yeah. So nice to see you after a long time.
Yes, sir.
Continuing to your presentation, I actually, but 6 months back, I was in Wales.
Okay.
I stayed in my relative's house for about 15 days.
Okay.
At the end of 10th day, they took me to a waste disposal site.
Okay.
It was very interesting. They carried batteries, separate cover, and
Yes.
old mobile phones in separate cover, and
Yes.
asked me to put it to a separate bins in a recycling plot.
Yes.
So it's very interesting. Actually, we should also follow. If not, say we went almost 10 kilometers from their home to drop those things. They do once in a month. So I think it's a good case study. We should learn from good things. At BBMP or somebody should plan some waste recycling bins, especially for disposing maybe near each park in Bangalore or something like that, and educate people. And there is a important need to put these things as advertisements in newspapers as well as in the TV media. Educate them how what you said, how it is causing a lot of pollution problems to the environment. That we throw tube lights, where so many things we throw into dustbins. This is finding way into the water and wastewater stream directly or indirectly, causing so much of income. Pharmaceutical industry is making huge money because of these inefficiencies.
Correct.
We go to doctors, we go to so many things, we lose so much of man hours, we suffer so much, but we not give importance to this because we are not able to quantify these problems actually. So there is a critical need from the government side, according to me, to educate people what you said in the media.
I agree completely, sir. One of the issues we always face is that the time for the effect is offset from the time of disposal. So
Correct.
when we are throwing away the tube light, we don't really feel anything bad because nothing immediately happens.
Yeah.
But we are talking about potentially getting some heavy metal 6 months later, 2 years later. We don't make the connection. And when we don't make the connection, we forget about it.
Yeah.
So as human beings, we are always used to making a very good response to acute things. But things that are not immediate or acute, we don't respond. And these things are actually in some ways more dangerous. And I think the UK has been doing this for many years. I was there between, I think, what was it, 2004 and 2010. Even the disposal of a mattress, you had to book. In those days, you had to book it for a certain day. And on that day, you had to, whichever floor you may be on, you had to bring it down within half an hour slot. If you left it on the road, they would put a tape, just like the crime scene tape. They would put it around it and it would green and black tape, just like a crime scene is yellow and black. They had a green and black environmental crime scene. And they would go to CCTV footage and the fine was enough for you to lose your house. That was how serious they used to take it even in those days. Even Scandinavian countries, they have realized that the best person to solve this problem is the person who is disposing, because nobody can predict what you want to dispose when you want to dispose. So once you want to control that, you should take responsibility. And if that means you have to drive for 10 kilometers, so be it. If you have to segregate it, so be it. Unless we take personal responsibility, the government can educate us, but ultimately we have to take personal responsibility for our actions. And in terms of education, the government has to do more. I agree, because today education and awareness is the first step.
only when people know about it that they can do something about it. And many people don't know about it.
Yeah, many people doesn't know. That is the problem. And see, after COVID, they are putting so much of fines for even not putting masks in the community. So similarly, if you put fines for not inefficient disposal, it will come. The people will come to know.
Correct. I agree.
There is a means to do anything. We have to have a will. That's all.
Exactly. Any other questions? I haven't checked the chat, but I don't think there are any other questions on the chat.
TV Murali has raised his hand. Murali,
Okay.
Sir, you can unmute and ask your question.
Yeah. Good afternoon, sir. I'm Murali speaking.
Good afternoon, Murali. Hello.
Sir, you are able to hear?
Yes.
Yes, I am Murali, assistant professor. My question is that in hazardous chemicals, that is hazardous metals present in the electronic items like a cadmium and lead and other metals, how you will be having the integrated method of separating out from that electronic items? Hello?
Okay. Yes, my
thing is that this is hazardous and also it is not safety to the human, and it is having many chemicals and other things are present in the electronics and other things. How will you, in what method they will separate and refine that materials?
So I'll try and answer as best I can. So the way e-waste is today, that it's designed to be perfectly safe for the consumer to use, as long as they do not modify it, right? So when you go to buy a computer or a TV, you don't get a safety warning that this is dangerous, because most of the hazardous materials are bonded in such a way that for normal conditions, they are not going to be entering the environment around them. So we can repair them, we can open them, we can even resolder some component, and it's still not hazardous. When they reach the end of life, that is when the complexity starts. And you're absolutely correct. You have cadmium, you have lead, you have mercury in certain switches, and these may be distributed in very, very, very tiny components. So the way you have to think about this is that rather than thinking about this as some sort of e-waste stream, this is nothing but a complex ore. And the ore needs to be treated just like you would treat an ore that you are mining from the ground. You need to increase the concentration of the material that you're planning to recover in different ways. So, for example, if you're talking about lead is typically present in two places. It would either be the battery, which may be a lead acid battery, or it would be a component of the solder, typically mixed in with tin. So it's distributed in the soldering. So when you're trying to recover lead, you will take out all the other components, the steel casing, the aluminum, the wires, which are PVC plus copper, and you will give the components that are rich in lead to a lead specific industry. The lead specific industry then has the capability to monitor for lead, to understand how much is going in, to make sure that their workers are not exposed to lead. Similarly, when it comes to cadmium and others, the amount in e-waste is very small. And so what happens is they usually go for the ride with copper. So your copper becomes the dominant metal, and these other metals, whether it's cadmium, whether it's rare earths, whether it's gold, whether it's silver, whether it's palladium, these become the passengers. So copper recycling plants have to then add on the capability of either recovering these metals and purifying them, or at the very least treating them safely. So if you look at e-waste as a source of metals, your job now is to make each ore concentrated in some way. So if you remove the rechargeable battery, that will give you lithium, that will give you cobalt, that will give you nickel. If you remove the PCB, that will give you copper, gold, silver, palladium, maybe some heavy metals, and maybe some lead and tin from the solder. If you remove the wiring everywhere, then you will get copper plus PVC. Once you break the material down into less complex streams, individual industries are able to handle it because the scope is less. However, you will still be left with a fair degree of complexity in the printed circuit board. This remains the biggest challenge because you have hundreds of metals in a small device, which now is more complex to handle. But that is usually handled by big companies that have a reason to do it because the value is also there along with the risk.
Sir, Mr. Amit has a question. Which one is more hazardous, industrial waste or e-waste, and why?
So again, it's a hard question to answer unless we know what kind of hazardous waste you're talking about. But if you look at the rule book, or if you just take a simplistic view of it, typically hazardous waste as defined by the rules will be more dangerous. And the reason for this is that if it's defined as hazardous waste, it's likely to be concentrated when disposed by the unit. So let's take an example for maybe an electroplating unit or a chrome plating unit. So you are going to buy a car or a bike and your mirror needs to be chrome plated. So they chrome plate your mirror. And to do that, they have a chromium solution. And at the end of the day, they have this bath of chromium and other metal rich sludge that needs to be disposed. This sludge is defined as one potential hazardous waste. It is very concentrated. Whereas if you open up a battery or a CPU, you will have many metals, but the concentration of each of those will be much less. So the simple answer is probably the hazardous waste, but the specifics of each stream will dictate how dangerous it is. And as an old boss of mine used to say, when you are doing engineering, the devil is in the detail. So we cannot afford to be lax. We cannot just use words, we'll call this hazardous waste, or we'll call this e-waste. What do we mean? What are we talking about? What are the concentrations? The devil is always in the detail. And as engineers and as people who are in this field, we need to educate other people to appreciate the detail. When you're disposing something, understand what you're disposing. Don't say that I'm throwing a plastic. Which plastic is it? Is it recyclable? Which metal? Today, how much of our country, in terms of a percentage, knows what they are dealing with from a material perspective? And so this is part of the problem Ravi Shankar sir was talking about. We need to educate people to be clear, to understand, so that they can learn. I am disposing steel. I am disposing copper. I am getting a filling, or I'm buying jewelry. What are they using to make my gold hard? Is it cadmium? Many times cadmium is used in jewelry and people don't even know. And they may be putting the jewelry in their mouth, they may be eating from it, and they may be dealing with cadmium. So our population needs to understand detail. And if you want simplicity in life from your materials and your electronics, you have to be comfortable to learn the detail, because the detail is coming for the ride, and the devil is always in the detail.
Uttam, can we tell that industrial is acute and e-waste is a chronic?
In some way, that's probably a simple way of looking at it. So that the industrial, because of the concentration and the volume, the industrial is acute, and e-waste is likely to be chronic because the volumes are smaller and the hazards are more lightly distributed.
Yeah, that's what I thought to conclude your talk.
Rashmi,
your answer, sorry.
Sir, Professor Rashmi Rameshwari has a question. Solar power batteries after some time will be replaced. Kindly throw light on how it will impact us in future. Solar power batteries.
I think that's a great question. Actually, today's e-waste rules, Rashmi, do not address solar at all. And in fact, the big gap in the legislation framework is that you have battery management rules, which are being amended this year, but they were written primarily for lead acid batteries, the ones that you have in a house with a UPS. And there is no coverage for nickel cadmium batteries, and there is no coverage for lithium ion batteries, which is almost all the batteries that are associated with power banks and e-vehicles, and also many times with solar installations. So when you look at solar, there's two problems. One, there is no legislative coverage for the panels, and solar panel waste is going to be huge in this country. So we are talking about panel lives of about 15 to 25 years. Many panels have cadmium. So somebody asked me a question about cadmium. Cadmium is one of the primary materials used in a certain kind of solar panel, and cadmium is very dangerous. You also use PVF, polyvinyl fluoride, to make the backing sheet. You use adhesives like EVA, forget what it is, something vinyl acetate. Someone else will probably know what it is. So solar panels, when they need to be recycled, are extremely complex, and the recycling chain doesn't exist. The batteries that go with them can be one of two types. If they're lead acid batteries, actually lead acid batteries are very simple. You have a PP body, you have lead electrodes, and you have sulfuric acid as your electrolyte. And there is a pretty strong secondary lead industry in this country. There are two giant companies. One of them is called Nile. I forget the other one, Gravitas India. They do thousands of tons per year of lead recycling. But lithium-ion batteries have a lithium electrolyte and typically a cobalt cathode. These are not recycled currently in our country at all, and the infrastructure to recycle them doesn't exist. So at the end of the life of a solar panel, assuming that the battery is also going to be replaced, there is a huge gap in recycling. And the short answer to your question is, today we have no infrastructure for any of these things. And it's critical that we start looking at it, because the panels are already starting to come. Because we are so aggressive on installation of solar, because now it's cheap. The panels are coming at a cheap rate. Our prediction is 15 to 25 years life. But I have seen tons and tons of panels in the market available because we haven't predicted hailstorms. We haven't predicted damage. We haven't predicted transport damage. So this is already a waste stream that's accumulating that requires urgent solutions.
M.S. Govardhan, Professor M.S. Govardhan, do you have a question? Please go ahead quickly. Or kindly mute yourself, please.
Is there anything in the
questions?
Anything in the chat that I've missed, Sri Lakshmi?
Pretty much, I think we covered everything, sir.
Okay. Oh, there's someone who asked about CFL and LED bulbs.
Yes.
This is Dave Kikoli.
Dave Kikoli wants to know about, yes.
So CFL is very hazardous. CFL, Devki, has phosphor for the luminescence and mercury, and both those are pretty nasty. So CFL is a very, very toxic waste stream. LED is smaller, but is not less toxic. It has many toxic elements in it. And again, LED was expected to have a very long lifetime, 15 years. But the data that we are seeing suggests that it's not much higher than CFL. And many of them have, for example, arsenic and other metals in them. So equally toxic. But with CFL, the biggest concern is mercury, because mercury is such a nasty metal that that makes CFLs particularly bad. Someone else has asked financial and logistic requirements for setting up a recycling plant. Just like in any other space in the recycling industry, the financial aspects really will depend on scale and security of supply, both of which are unpredictable in recycling. So unlike any other chemical plant where you can go out and buy your raw material, whatever you're making, you're going to buy a raw material from a supplier. In recycling, your raw material is unpredictable. Someone may dispose it, may not dispose it. You may want a TV, he may give you a fridge. So that makes the financial planning extremely difficult. And you're absolutely correct that logistics is a major issue, and formalization of the logistics. How do you pack tube lights? How do you separate batteries so that they don't catch fire? How do you ensure that the terminals are taped? This is an important thing that, as a company, we're learning today. The important thing is that at current conditions, most recycling plants are financially unviable on recycling alone. And that's true for Alexion as well. Unless we do refurbishment or resale of certain IT and other products, on recycling alone, financial viability doesn't exist. And this is a combination of raw material pricing and absence of incentive from the government. And those are two things that need to change if you want to see a demand or you want to see expansion in recycling capacity in this country.
Uttam, I have a question.
Tell me, sir.
This since somebody asked about CFL and LED, see there is a earlier conventionally we used to have a incandescent, and later it came with CFL, and again they have come out with the LED. Then I read some of the literature. There are some psychological stress and effect due to LED, and even there's toxicity containing in LED is a big problem. The Swachh Bharat we have started, and we are not told what to do with the disposal actually. Only the government told that you have to do Swachh Bharat, open defecation has to be stopped actually. So they have not given any provision for networking this sewer line to some common treatment or whatever it is. Okay, these also is making, see, these people are making rules and regulations and not thinking the end problem. See, I was read in some of the literature or news, this LED has got a lot of psychological stress. What is the say on that?
So actually, IPCC, the climate change body, one of the governing bodies for data on that, recent studies have now added light along with CO2 as one of the largest human pollutants on Earth. So the newest research has suggested that along with producing much more CO2 than the Earth is capable of bearing, we have produced much more light than the natural species are capable of bearing. And that this is having significant impact on biodiversity. In the case of LEDs, this is particularly true because the wavelength at which they are operating is causing excess blue exposure for species who are not used to it. And so many studies have shown that LED wavelengths are unsuitable for natural species, whereas the typical incandescent bulbs are more similar to the sun and therefore had more a natural match for humanity. So we are doing this continuously in the sense that we are solving problems one step at a time, and then we are creating new problems. Just like you said with open defecation, solving the problem of putting a toilet, but we are not solving the problem of how to treat the waste. In the case of light, we are solving the problem of power consumption, but we are not able to make that light easily recyclable or of a good match for human frequencies. So I think the issue is that as engineers, as policymakers, as a civilization, we are yet to we give too much credit to ourselves. When we invent an LED, we say we've solved a problem. We don't predict the problem it may cause, and we don't try to look at the problem holistically. And in environmental science now, it's been decades since we've been looking at life cycle analysis. But how often do we implement those philosophies to problem solving ahead of time? We don't do it. So we invent an LED and we celebrate and we say, let's change all the CFLs. So we do two things. Not only do we introduce a new waste stream, but we also suddenly dump huge amount of mercury, but we don't account for it. So I think continuously human civilization gives itself too much credit whenever it does something. We invent the car, we say we're amazing. We invent the rocket, we say we're amazing. But every time later, now we say we have a huge problem. So how can we be amazing and have a huge problem? So I think a healthy dose of reality is required when we make scientific progress. And that scientific progress should be tempered by our impact. What is the impact that scientific progress is having? And have we considered that impact when we have taken that scientific progress and scaled it? It's a bad parallel, but the atomic bomb is one of the cases where this whole cycle was compressed. We did something, we invented something, we used it, we saw its impact, and we shocked ourselves. And all that happened very quickly. So we were able to learn that, we thought we did something good, but actually we did something terrible. And we learned that within, I don't know, 2 or 3 years. But in almost every other invention which we have pushed into production, the time scale for us to learn that is elongated. And so we celebrate early. And I think part of sustainability and part of the challenge for all of you as teachers and all of us as engineers and entrepreneurs is to question ourselves more thoroughly in terms of how we're approaching problems and what are the long-term effects, and whether on the balance of probabilities, whether this is really good or bad. And I think we need to increase the time frame of evaluation of everything we do, whether it's a political, progress, whether it's social progress. Our our evaluation time frames tend to be very small. 1 month, 6 months, 1 year, 5 years for a government, 3 years, a payback for your FD, 1 year for your FD. But are we too early in our evaluation? Should we be taking more long-term view for everything we do? And I think that's an open question. And in my opinion, that is really something that we need to bring in culturally with the next generation, so that they think differently from us, and that they challenge innovation in different ways. We have typically challenged it only economically. Is it cheaper, and does it work? These are the two things we've always asked ourselves. This is what we've asked ourselves for every innovation, whether it's medical or engineering. Is it cheaper? Does it work? But are those questions enough? What other questions should we be asking? And I think that's the civilizational challenge we face today.
Yeah, thank you, Uttam, because
Thank you.
Yeah, you can go ahead, madam.
Yes, sir. Thank you, Dr. Uttam, for your talk on metal circularity and circular economy, make, use, and return. So you threw light on e-waste and metals like copper, aluminum, and then mercury, and then the relation between critical materials and energy production, and then how India is doing a great job in recycling. However, it is lagging behind on resource recovery and disposal. Thank you so much, sir. The interactive session was also very well done. All the questions were answered. Thank you so much.
Thank you. I think just a short, for those who aren't following the chat, EVA is ethylene vinyl acetate. That's the one in the PV membranes. Thank you, Roxana. So thanks for the opportunity to talk to almost 200 people today, and I hope you found something useful in the talk. And thanks, CTP sir, for giving me the chance to talk to your audience. Thank you, everyone.
Thank you, sir.
Thank you, Uttam. Actually, it's a pleasure having you again and again in the department, actually. So your contributions to the department is really, maybe I cannot maybe equate it, actually. So thank you for all your support.
Welcome,
and,
sir.
And for your time, okay? And
Welcome,
hope all our participants, teachers have got benefited from your insight.
Thank you.
I'll catch you up later.
Yes, sir.
All the participants kindly share the feedback for day 1, session 2. Use the link provided in the chat box, please. Thank you, sir.
Good, yeah, Uttam. It was nice presentation.
Thank you, sir. Thank you, sir.
So nice to see you.
You too, sir.
2 decades, sir.
I came and saw you for that signature, no, sir. So I saw you
correct.
Recently.
Yeah, correct.
I'll see you in the afternoon, sir. I'm sitting through your talk. I'm curious about it. So I'll be there.
So nice.
Okay.
Thank you, sir. Please join at 2 o'clock, sir.
Okay.
I think 45 minutes is there. I think hope all the participants can have sufficient time and come back.
Thank you.
Thank you.
Please use the same link and the password. I'm going to end the session, actually. Again, I'm going to restart at 10 minutes.
2 o'clock, right?
Yeah, 2 o'clock. But however, this is on from 1:50. Thank you, Tom.
Thanks.